Yeah. Um, we're trying to prove symmetry. So assume that A is related to B. Sorry. Then there exists some some K, some I, some non-negative integer I such that Fi is equal to B. That's one, right? And so the whole idea is we want to go from A to B, and that's gonna take I times. But we also want to go from B back to A, but in a smarter way, which is taking some R and minusing some J to get back here. So that's equal to some R. We need to show this rigorously. The usual way that you could set this whole thing up is, hey, how do I go from J back to I, right? Like, how do I go from here? What can I do so that I can go to I, and it'd be J R minus J gets me back to I times. How do I say this in a way where it's like R minus J is the same as going to I, right? Like, if I go from A to B and it takes me I compositions, and I go from B to A and it takes me J compositions, and so it takes me I plus J times to get me to A compositions again. That's assuming that everything, like, it's larger. So this is assuming that we're taking some multiple of R, taking some multiple of R, so J itself could be rewritten as J is equal to R minus I. How the fuck do I explain like that? Right? So some number of compositions of A gets me to B, and some number of compositions of B gets me to A, but I need to show it rigorously. Let f of J be the times it where input B equals the steps that it takes for me to compose our number back to A, right? And we need to show that, right now there's no rigor because J could be anything. It could be going backwards from I, right? So it's completely different. But if we say that, hey, let R be some multiple of the cycle from f of A goes to A. Like, I know that because from okay, I'll write this differently. We're gonna say from part A, we know that from part A we know that there exists something here where there exists some positive integer k that's at least larger or equal to 1, such that we go from the composition of a back to a. Some k larger than 1, such that f to the power of k of a gets me back to a. So then how we need to quantify this with rigor. Guys. Some f of j, some value then it must be that. F of some r minus j is the same as the distance from I, right? Right, which is equal to I here. Same distance from so same distance from A to get to B. So that's the distance that we're going from A to B. But now we're gonna write from B. So we're trying to go from kill me. We're trying to go from B to A, and we're gonna substitute this is the same as f of I is it f of j? No, it's f. Okay. It's actually f of j. Right? We're just trying to rewrite this in a little bit more rigor, so that if I go from some f of I, how the fuck do I write? No, I'm gonna start by saying f of some j of b is also implies that it's f of some big R minus I, because we know that I plus j equals R, right? Here of b, and then we also know that this could be rewritten as f of I here. So it's the same as saying f of R of I composed by f of I of A is this f of R of I of B is the same as f to the R minus I times f to the I of A is equal to the f of R of A. And that's how we show that the rigor part is equal to A. So we just went from some B input here that goes through this big machine of compositions, and it's gonna spit us back A. And so that's why B is related to A. Okay, so for transitivity, we're going to go from assuming completely different case that A is related to B and B is related to C, and we want to show that A is related to C. So this is a lot easier, but you're just adding the compositions. Then there exists some I and j that's larger than 0 such that f of I of A gets me to B, and f of j of B gets me to C, right? And then, so f of I, f of j of B, sorry, f of j is on the outside, and f of I of A gets me to C. It's equal to f of j plus I of A is equal to C. So, A is related to C. Fuck. Okay. So that's fine. Okay. Kind of know the proof. Let's just place it here. Place it in the corner somewhere. And then just that we know is something that we can just like basically try to understand. Okay. We are good with the proof. We will continue. Okay. What's the smallest number of edges that we can delete from a complete graph K92? What is the smallest number of edges so that the resulting graph has an Euler-Tor? Well, then Euler-Tor is that Euler-Tor is you have to go everywhere and go back. So everything has to have at least like everything has to be like even degree. Oh, by the way, final exam, we have access to notes, so we can just pull the notes out and just like the info's on the notes. I hope that we search Euler-Tor here. The necessary condition for Euler-Tor is that if a multigraph contains an Euler-Tor, then every vertex has to be even. And so we have K92, and K92 is a complete graph, and so K92 is complete. And that means that we have got 92 vertices and 92 times n minus 1 degrees. 92 times 91 edges. Right, so it's just going to be this big graph with over 100 points. And then everything is connected to everything else. So it's just a mess. But every other graph has to be connected to every other vertex. So you could see why they have that many edges. So we have to delete the edges so that the resulting graph still is an Euler-Tor, and an Euler-Tor just means every degree vertex is even. That means for a K92 graph, the degree is, sorry, this is, the degree is n times n minus 1. Could we think of it as 91? No, it's 92 vertices. What do we know? What do we know? What do we know? What do we know? What do we need to know about a complete graph? Okay. So each vertex has degree n minus 1. Each vertex has degree n minus 1. So our 92 goes down to 91. So we have 91, 91, 91 for 92 graphs. For 92 vertices of the graph. Where's my music?
So I'm writing an essay on cats. Cats in art history. I'm an art history major and this final is due on Friday. Luckily, with Grammarly...
Shut up. Each vertex has degree n minus 1. Well, we want anything. We want every vertex to have even degree. Does that mean I have to delete 92 vertices? 92 degrees? So each, this is degree. Is that, and the edges is always half of the degrees. So we have 92 degrees worth. I'm assuming we can take away 46 edges. Okay, GG's. A simple graph has 46 edges. Can be removed to get K92 to all vertices with degree 90. I'm just gonna, how about I just like zoom that down? That just looks so fucking weird. Okay. Okay. Sorry, I have have bad handwriting. I'm gonna try to do this again. Fuck. Oh God. Oh God. Wait, let me see. Saying bop. Okay, that's fine. We'll just keep it like that. Yerp. Next proof. What does this proof say? A simple graph G has 34 vertices, is connected and planar, and does not have a cycle of length 4. Furthermore, the dual has an Euler-Tor. Prove that G has at most 48 edges. Are you shitting me? Dual of G has an Euler-Tor. That has to be something important, but I've never really touched joules and Euler-Tors. Has Euler-Tor, which means the degree of okay, if it has 34 vertices and it's simple, and planar. Jeez, what the fuck? What would a planar graph? There's a number for planar graphs as well. So I just need to know the number for planar graphs. Sorry. Sorry. G has an Euler Tor, and that's a what we there's too many things to know about Euler. G has G simple. Wait, 36 vertices. Okay. Sorry, 34 vertices. Connected and planar. Connected graph. Planar graph. Let's see what I need to know about planar graphs. Well, for a planar graph, ChatGPT does all my work for me. I just need to read. For a planar graph, it can be drawn on the plane without edges crossing except at their endpoints. For connected, do we have the number of edges? Oh, cool. Oh, cool. One regular is everything. Two regular is... That's a two regular graph. A three regular graph. Everything has three. Four regular, everything has four. Okay. Fuck. It has a planar embedding. So only thing we know is Euler's formula. How can I use Euler's formula? Euler's formula, and it has at most 48 edges. Oh, perfect. Well, if it's simple and connected, and the dual of G has an Euler Tor. Oh, if the dual has an Euler Tor, then that means that the number... Sorry, the dual... What's the dual do? The dual is all the... Yeah, we start with this, then we're gonna push in. The dual... Where's my dual? What's the property of the dual? Fuck, man. Fuck. What a crazy question. This one. Here, the dual of a planar map is also planar, so it has the same number of edges as the original. So That's the first thing we're gonna say. G, if the dual of G has an Euler Tor, that means that G as an Euler Tor means all vertices are even degree. Okay, that's one. Then if G it has even degree means even edges, right? Yeah. But I need to say that sum of degrees in a planar map equals twice the number of edges. Sum of degrees of all regions in a planar map. Sum of degrees of all the regions in a planar map equals twice the number of edges. There's one. Think. The degree of a region in a planar map is the number of edges bounding the region with an edge counted twice if both sides of it are part of the same region. All vertices are even degree. If G has even degree, then sum of vertices how the fuck? What's the max number of the edge bound is M has to be less than 3n minus 6. So that's the first part of Euler's formula. So we should use n v minus I'm cooked. Think about it. The number of vertices in normal G, the number of vertices in G dual is the number of faces in G, and the number of edges in G dual is the number of edges in G. Sorry. Oh, fuck. Think, bruv. All vertices are even degree. If the G dual has even degree, then the sum of the vertices will also be even. G dual has the same number of degrees as, same number of edges as G. Right? That's what I know here. Fuck this proof. This one. And it does not have a cycle of length 4. 34 vertices. 33 is the max degree for 1. Wait, stink. The dual has an Euler Tor, and it doesn't have a cycle of length 4. That means cycles of length. That means we can't use the other formula. What the fuck does no cycles of length 4 do? No cycles of length 4. Let's search length 4. Cycles. That's nope. 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 This one. Doesn't say. How do we apply this? How do we apply this? How do we apply this? I mean, that's what I need to know. The number of edges is less than 3 times the vertices minus 6. Okay, we're gonna apply that first of all. So the number of edges is less than or equal to 3 times the number of vertices, which is 34 minus 6. Okay, we just gotta hone down our number. So that's our first equation that we are thinking of. That means that 3 times 34 is what? 90. 102 minus 6 is 96. E is less than 96 right now. How do we push the bound down to at most 48 edges? That means that if G has that many, then the dual also has to have an even number. And so the dual is the dual has the same number of edges that G has, because it's like whatever G is missing, the dual has to have. No, that's the complement. That's completely different. Dual has an Euler Tor. If the dual of G, I'm gonna write dual like that, has even degree, then some of the vertices what's something that I need to know? I need to somehow visualize or mathematically show not having a cycle of length 4 and how that's supposed to mean anything. Not having cycles of length 4. Not cycles of length 3, no cycles of length 4. Okay, well, simple means okay, simple graph means n vertices n minus 1 degree max and n times n minus 1 over 2 edges. until we form an equation somehow. So 34, 33, 30, yep. Number of edges is 34 times 33 on 2. And dual Euler-Tor means all 34 vertices are even. So that has to divide, some number has to divide evenly. No cycles of length 4. No cycles of length 4. No cycles of length 4. Fuck me, bro. That's all I know right now about the graph. What else do I need to know? Okay, about in 2 minutes, if I can't do it, I'm just gonna ask ChatGPT. Okay, if it's planar, it must. The number of faces is 36. Is 34, sorry. Okay, I don't know. We're gonna ask our best friend ChatGPT. Ugh. Davaruski. I'm gonna need you to help me solve this. Right now, what I know or what I've inferred is that we're gonna use Euler's formula. So the number of edges has to be less than or equal to 96. Right? If it's planar, I'm sure there's like a if it's a simple and planar graph, maximum of 34 vertices, maximum of 34 times 33 degree, maximum of 34 times 33 on 2 edges, but we've already cut down to at most 96 edges. And they say, hey, it does not have a cycle length 4. So, and the dual of G has an Euler-Tor. So that's where I'm actually struggling the most. I don't know how to basically form those definitions for if it has an Euler-Tor, then all of the vertices are of even degree. Should I be writing an inequality and then finding some type of inequality? Cycle length 4, nothing. I mean, if it's not cycle of length 4, does it say something that I need to know? You're saying no cycles of length 4 is a 2 regular graph, right? Which is disjoint cycles. I haven't been able to really understand what that part really means. Oh, sorry. It says, does it have a cycle of length 4? So it's not disjoint. Hmm. What is ChatGPT going to say? The dual for Euler's torque means all the vertices have even degrees since there's no 4-degree cycle. Yeah, okay. You are on the right track with Euler's formula, but one important move is not the usual. Yeah. Let extra conditions improve the face size bound. Let the number of vertices be 34, the number of edges be small e, and the number of faces be f. Because it's connected and planar, it's going to give the other one? The fuck, man? What is this one then? For a non-empty connected planar map. Oh. A simple connected planar map and a non-empty connected planar map. Fuck me, I don't... Use the dual graph condition. The vertices corresponds to the faces. The degree equals the edges. The vertices of the dual graph G correspond to the faces of normal G. Yeah. So let this be the... Fuck. Let me just do an easy one. Right? If we're going to go back to faces... don't even... We're going to draw... something here, something here, something here. Right? Is that supposed to be something like that? You understand what I mean? I'm cooked, bro. The degree of a vertex in G dual equals the number of edges around the corresponding face of G. Since the dual has an Euler torque, every vertex has an even degree. Therefore, every face has an even length. Discrete mathematics. So every face has an even number of sides. Every face has an even number of sides. Because G is simple and has no cycle of length 4, no face can have length 4. In a simple graph, no faces. Not sure what that looks like. I'm gonna need you to show me images and help me visualize. to go from G dual to G. Dual having an Euler toward tells you the faces are even-sided. Okay, let's suppose that this is map of G then. Yeah, those are the faces or the regions. How about we just make this a little bit simpler? Just gotta revise on how to do this. This is one region, this is two regions, this is three regions. We're gonna connect this one. That's a loop. That connects, this connects, this connects. Have we crossed everything? That means we are doing something like that to here, here, and like that, and like that. Sunglasses. So if this one has, what did they say? What the helly? What the helly? What the hellio? Okay, that's a planar graph of G. 1, 2, 3, 4 faces. I'm going to put a vertex on each face. And I'm going to do the normal, good old normal, like, okay, so now we have a dual graph. The vertices correspond to the adjacencies of the faces. Okay? So like that. If G is connected, then G dual is connected if each vertex corresponds to a face. So if the degree of a vertex is equal to the number of edges, okay. If this is even, that means this has to be even? Is that what they say? Right. So the dual of G has to have an even number. Suppose this is even. Then this must have like one region here, and another region here. So that means the vertices have like 4 edges, whereas if this is the vertices, this goes back to the faces, then the faces are even. Oh, fuck me. Sorry. What did they say? The degree of a vertex in G dual equals the number of edges around the face of G. Okay, yeah. Like, I get that now. Right? Because they're saying, hey, if this is a point and there's 3, that means that face had 3. Oh, this face had 4. Okay, this one corresponds to this. Right? It has, this one has 3. It's like this. This one has 3, so it's like this. Ah, fuck. Therefore, every face has an even length. Therefore, every face has an even length. What do you mean even length? Like, every okay, there. Has an even number of sides. So if this is one face, that this has 4. And this is another face. Okay, let's draw something that looks a little bit more like what we're going to do. Like, that's gonna have 2 sides. Okay, we'll just draw it like this. Right? So here, this graph right here has all faces are even size, are even number of sides around it. All regions, we'll just call it regions. Okay. So because it has no cycle of length 4, no face can have length 4. And faces cannot have length 1 or 2. So they're just trying to rule out, hey, there's 1, 2, 3, 4, 5, 6. And we're going to rule out this doesn't happen. And we're going to rule out this doesn't happen. Hey, these 2 are odd. Hey, so that means that the number of length has to be at least 6. Okay. Now count face edge incidences. Each edge borders 2 faces. This edge is 2 faces. So the number of face lengths of regions is equal to E. Okay. Same as V is 2E. So sum of the, okay, that means sum of degree in G-dual is the same as sum of regions, right? Sum of regions. Sum of vertices in the map, the planar map of GeoDual is equal to the sum of the regions in G. And ruling out cases 1, 2, 4, the least is 6 edges around each region. So we are looking at a graph that looks a little bit something like 1, 2, 4, 5, 6, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So they're all vertices. Okay. Since every face has a length of 6, of at least 6, the number of Right. Sum of vertices in dual is equal to sum of regions in G. And ruling odd cases 1, 2, 3, 4. The least is 6 cases surround each region. So how do they go back to edges? So regions. Oh my god, what a fucking sick inequality. Wait, so why didn't you use my inequality and use the normal Euler's formula? Was my inequality used for something else? Or why specifically using Euler's formula at that specific time? So this is incorrect. What a crappy proof, bro. We need a stronger argument, and somehow you made a strong ass argument with R plus the number of regions plus the number of vertices is equal to the number of edges plus 2. Then that means the number of regions plus 34 is equal to E plus 2. And that's equal to 32 is equal to E minus R. Could I do that, or should I just do plus? No, we're trying to find something for R here. Starting, okay. So that's one of my first steps for the setup. Sum of the odd vertices of the G dual is equal to the sum of regions in G. That means there has to be at least 6 edges around each region in G. Then the number of edges or using what we know, sum of vertices is it sum of degrees? No, I don't remember this from anywhere. I thought it was the degree of the vertices. Where do you get that formula from? 6e is more than or equal to, larger than or equal to 6f. 2e is larger than or equal to 6f. Oh, I'm almost there, guys. I almost get it. If I get it, I get it. There are two different degree ideas happening. In the dual of G, the vertices respond to the faces. Yes, I get that. So the degree of the vertices are the number of edges. Oh yeah! But didn't you say that each... It was like the sum of the degrees? So, yeah, that just means like each degree of G has to be at least... Imagine a cube. Each face is a square. So each face has length 4. So the total face length is 24. Now I'm gonna need... Hey, hello. I'm gonna need you to convert or like try to rewrite the expression in a way such that we'll be working with the vertices instead of the 6 faces. No, not really. I still don't understand why it's only 6F and it's not the sum of all the Fs. Like the total like the total degree is n times n minus 1. And so how about you like try to talk about that? And then the number of edges is n times n minus 1 over 2. So 2 of that is the same as... But like 6F is... What the fuck is 6F, bro? It has 12 edges and the face length is 6. Oh my god, I'm fucking going crazy. I don't... What the fuck, man? Không hiểu, chưa hiểu. Yeah. Sum of face lengths is 2e. Yep. For each edge has 2 endpoints. So when you count the vertex degrees, each edge is counted twice. For faces, each edge has 2 sides. Yeah. Suppose there are 6 faces. So there's the sum of 6. Okay, it's 6 times the number of faces. Thank God. Thank God. Thank God. Thank God. Okay, so now we just gotta write it our way. Right. Right. So... Start with 1. If go to here. We need these marks, brother. Okay, we're gonna start with 34 vertices. We get the goal now. If G has 34 vertices and is connected and planar we can use Euler's formula that the number of regions plus the number of vertices is equal to the number of edges plus 2. And V is equal to 34. So we have an inequality, an equation for R plus 34 is equal to E plus 2, and that is equal to we're going to minus that, so we're trying to find something for the regions. R is equal to E minus 32, which implies that R is equal to E minus 32. We're going to interchange this. So that's our first checkpoint. G dual has the same number of edges as G and has the same number of vertices as G has regions. So fuck. And has the same number of G has the same number of edges as normal G. And every vertex of G dual is the number is every region in G. Right. Since G dual has an Euler tor, every edge in every degree vertex of G dual has to be even. So converting from G dual to G, every face of G has to have uneven number of edges surrounding it. So let's assume we have something like that, and we have, it's just this and this, sorry, just this, right? So assuming you have this is G and then this is G dual, so we're just going to make some inference about G dual, right? So we're going to draw something like that to G dual. G dual has this, it has that, and then we're going to connect this line, we're going to connect this line and this line corresponding to here and here, connecting this line, 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 connecting this line. Okay, I'm going to draw something like that right now. So we're going to go here, 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 here. That looks so dope. Don't worry. Sorry. Once again. This. 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 And this. So it has 3 on both sides. Yep. We'll just draw something like that and something like that. So, okay. So every face of G, every face of normal G. So vertex of G has to be even. So converting from G to G, that means it has to have an even number of edges surrounding each face. Right. If you have a face here, why can't it have 2 edges? Okay, my last question. My last question is, why can't the regions have 2 edges? You said it can't have 1 edges, because yeah, I can understand that, but why can't it have 2 edges? Because if, yeah, why? What's the idea about, about it being simple, about being simple, so there's no loops. So G, but what a fucking crazy question. But since G is a simple graph and loops are not allowed, what I'm going to do after is I'm going to write an outline. And loops are not allowed. But since G is a simple graph and loops are not allowed, fuck. It must be that can't be 1, because it can't, like the face can't be 1, and you can't have loops, and it doesn't have length 4, and every vertex at every edge has to be even, so it must have at least 6. Oh my god, what a fucking question. Such a retarded question. I hope it comes out because I studied my ass off for this question. Since G is a simple graph and loops are not allowed, there can't be two edges between a vertex. And since G prime has to have even lengths, G dual has to have even lengths and no cycles of 4. The least amount of edges surrounding a face is a region. Region is 6 edges. Then we have another inequation for where the sum of all the faces is in of all the regions must be equal to twice the number of edges. Since it's at least 6 edges per face per region, we have since it's at least 6 edges per region, we have the sum of the regions must be more than or equal to 2e. So let big F be the number of faces, and 6F be the expression for at least 6 edges in each face. Okay, perfect. Did you hear that? That's pretty sick sound. Then this part is 6F larger or equal than 2E. And 6 R. Let's call it R. Around each region. So I think I know how UNSW does their test now. They put all the core up first. Like even for the questions of the core, they put it up first. Then if we do like one or two times of these samples, we'll get to like we'll grab like the other 15-ish marks out of 20 marks from the unseen core, and then if we do try to go up and beyond, we could ultimately get like another 10 marks from the full bank. So like I would want to be doing having exposure to most of the bank first and then revising most of this, because these ones I know will come out, and the other ones, as long as I have exposure to them, I could probably have a crack at them again. Yeah, I wouldn't do it any other way, honestly. Like I wouldn't do these ones first, because like right as we like the chance of these coming out is high, so we want these to be as fresh as possible. The other ones, just as long as we can have a crack at it, we can do it. Right, like these proofs I need to really know. Right, 6R is larger than 2e, so substituting what we know in here, 66 times 32 minus e, larger than or equal to e, 196, sorry, 180 plus 12 and 192 minus 6e, larger than or equal to 6e, plus 6e, 192, 8e, divided by 8, 192 divided by 8, 24. So we get 24 edges, so most 24 edges, and is that sounds weird, 48 edges. Sorry, it's E minus 32. Look at me.
Okay, you're watching YouTube, but did you know there's a YouTube music app?
I'm not ready. Usual lipstick.
YouTube Music Premium.
Right. 6e minus 192, larger than 2e. Minus 92 is larger or equal to minus 4e. Divide that by 4. That means the most number of edges is, that's supposed to be 48. So G has to have at most 48 edges. That was good. So the biggest things that we have to remember is that this part was kind of the hardest. And loops are not allowed. Boom has to have even lengths and no cycles of 4 is right. And regions, so R be the number and 6R, and we go from here to here and solve. What a fucking question. Could I kind of replicate it? Probably. Jared wants to fill a 2x14 grid with 2 rows, 14, yeah. Two by 14. From 1 on 2 tiles, number from 1 to 14, and unnumbered squares. Jared may choose more than one of each type of tile and does not want to rotate 1 or 2 tiles since the numbers should be upright and readable. How many ways can Jared tile the 2 by 14 grid? So, choosing more than one of each type of tile. No rotations. Ugh. 2 by 14. This is a combinatorics question. Matting. Where every time he chooses that small tile, he basically has to choose a small tile underneath or above, so that forces the choice. So how about we just call it squares, and he has 4 choices for each, so like 16 choices for each square. Each numbered square. They're doing 214. If I line up all of them, 2 to the 2 times 14. How would it even? Yeah, let's visualize it, because I can't visualize it. One, that's like a block, a block, a block. That's a 2 on 6 right now. What's that? 8, 10, 12, 14. Oh, my bad. My bad. We can do it. So 7. Let's just call it 7 squares. Yeah. So, and yeah, so this is like a it's like a tiling. Like I choose a spot to put it, and then I can choose a spot to put it, and then move on to the next, which is a combinatorics question. C7 choose 16 times C7 choose 2. No. Uh, 16 choices for each numbered square. Right? Like I could put a block there, and I have 4 choices each to choose from. Or I could put a block there, or I can put one here, and this one is just completely covering. I can put all 7 choices of the block, and everything else in between. So it's this one. Hey, this tile. I don't know. I'm not good at combinatorics. Let's practice. Oh. The death of me. Combinatorics. Okay, this is what I have right now. I know that it's a 2x14 grid, so it's a horizontal grid, and the tiles are not overlapping. And let's say if I put a horizontal tile down, I've got 4 choices. But if I put it either like on the lower end of the 2x4 grid or the upper end of a 2x4 grid, it would force me to one of the other 4 choices of those 4 horizontal tiles on the upper. So I would just like assume that, hey, in each there's a 2x14 grid, so there are 7 2x2 blocks, and there are basically 16 choices of a block, and there's a 1 choice of a just like an unnumbered block. That's all I have right now. Give me a hint on the next step, but don't give me the answer. Like what should I do next? Well, combinatorics is awful. Yeah, getting to these questions is painful. Is painful. Really, it really is painful. It's really hard. Combinatorix. Combinatorix. Let's actually use the tile. Ordered sets with repetitions. So this is ordered sets with repetition. What, like? Fuck, man. It's like lining people up. Like this one, it's like putting stuff on tiles. Like I can feel myself almost cracking the code to like those tile ones. We're choosing a place for cat 11 ways. It's like I know I have two choices, but then because I'm doing it like there's like 14 for the second choice and one for the other choice. That's the weird part. Permutations? Why the fuck would it be permutations? Your idea of 2 7 times 7 blocks is too restrictive. Fuck. A 2-on-2 tile fills 2 columns at once, but 2 horizontal tiles stacked also fill 2 columns. Yeah. So a 2-on-2 chunk has 17 ways. The issue is that the tilings do not have to split neatly into... Yeah, it does. Is not 17 to the 7? Oh yeah, I could just think about it like that. Why did I think... yeah. But it's not this. I don't know why it's not that though. It is that, you fucker. It's actually 17 to the 7 ways. So, okay. So it is like choosing one of the two. I need to remember, hey, okay. So it didn't click, but it would be the... It's like the choices and the... No, the ways and the choices. $17 since the unnumbered box is one way, and there are 16 other ways to get to fill the 2-on-2. Block. There are 17 total ways for untiling. Oh my god, ChatGPT just said, hey, you're exactly right. Yeah, you can't really shift the tile set just because, yeah. There are 17 total. What I want to do today is make sure I get through all the questions and then do all the combinatorics in the big problem set, just to make sure like I don't get any combinatorics wrong. Like everything else I'm not too scared about, but combinatorics is like retarded. Sorry, bad word. Ways for one tiling, and we will make 7 independent choices. For it. Therefore, 17 times 17 times 17. I'm just gonna visualize this in my head. Give me 1 sec, because I'm trying to learn something. Hey, 17 ways for me to fucking... Here, I want to visualize right here. Hey, I've got 17 ways here. And this next one, I have 17 ways here. And this next one, I have 17 ways here. And this next one, I have 17 ways here. And this next one, I have 17 ways here. And this next one, I have 17 ways here. And this next one, I have 17 ways here. Therefore, 17 to the 7 ways. Oh my god. Ah. Kill me now. Okay. Jared accidentally purchased 3 of the 2-on-2 tiles and therefore can only use at most 3 ways. In how many ways can Jared tile the 2x3 grids with this new restriction? Okay, so now there is like finite repetitions. How the fuck do we finite repetitions? No. There's a principle, There's a principle of inclusion-exclusion for counting the elements in a union. There's an inclusion and exclusion formula for any finite number of sets. I mean, I could do it by hand and say, hey, there are these possibilities. I mean, that would be, hey, if he had a finite number of 2-on-2 blocks, like 3, then there are cases. So the first case is he doesn't use, right? Doesn't use. Which is 16 to the 7. Second way is uses 1. Then use 1 and okay, there's some over counting. I can feel it. I can feel it already. Is it inclusion exclusion then? It's unordered sets. It's unordered sets. Think about it, think about it, think about it. Here. You have the problem of choosing different objects from n objects. Fuck. Fuck, man. Give it a think, Jaden. You can use at most. And then it's what's an at most thing? What's an at most question look like? This is it. These types of questions. Here, the number of words with exactly one vowel. Next, we count with 3 vowels, and those with 3 vowels. A word containing at least one vowel, if it contains 1 or 2 or 3, so the final answer is obtained by adding these 3 partial totals. So I think could we do that one? We wish to count the words with no vowels, and there are 23 to the third of these. Why? 23 to the third. Yeah, so it's like this type of question. It should be the easiest combinatorics question. Like, so there's 2 methods to the, what do you call this one? Unordered, what is this? Counting. It's normal counting. Here, yeah. 16 ways to choose the next 6. But I need to see why it's 20. It's 17 to the 7 ways. Subtract ways where why was it to the third? To the third. We do not wish to count the words with no vowels. I do not want the words with Okay, it's better to just do the partial totals. Okay. So my doesn't use or uses 1, then 1 times 16 to the 6. So this is, there's 7 ways to choose, right? C7 1, then 16 6, or uses 2, then C7 choose 2, then 16 to the 5, and 4 uses 3, then C3 choose 7, C then 16 choose 4. Brother, 16 choose 6, 7, sorry, plus comb 7 1 times 16 choose 6 plus com 7 2 times 16 choose 5 plus com 7 3 times 16 choose 4. Please be right. Oh, let's go! Is there a faster way to do this? 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 Or what? You may use at most 3 blocks, so choose how many tiles are used. So the remaining 7 minus K blocks or horizontal pair blocks, each with 16. That's the same shit, bro. Wait, are you saying the sum of 7 choose 3? Oh, that's fine. So that means that was the usual way people would do it. We think this through, it's fine. Jared has decided it is bad luck if 2 squares are adjacent. That means I have to make a choice, and then there are less choices. So instead of ordered sets, yeah. Could I do all of this, subtract the times that they were adjacent? Nope. Adjacent. Adjacent. No two tiles touch. No two tiles touch. No two tiles touch. Think harder, Jaden. What the fuck? No two tiles touch. Choose one. Or choose two minus something. Or hey. Hi.
Hello.
Hi. I'm streaming.
Ai hỏi?
Oh. No.
Ủa mai thôi hả?
Monday.
Mai.
Monday. No two tiles must touch.
Ok, bye.
Bye.
Long.
What?
Ai hẹn á? Long nha.
No. Don't click it. Don't click it. Ah, nice nails. Don't middle finger me. That's crazy. I like your nails. Good job. Good job for doing them. You saved yourself $100. No two tiles touch.
Ok, bye.
Bye. Say it again.
Ok,
Choose all.
bye.
Don't leave. If you're gonna call me, call me.
Ok, bye.
If you're gonna call me, call me.
Ok, bye. À, bye thì tao gọi em đây.
Okay. Bye, love you. I don't know. I don't know this question. Like, this question is... I'm cooked with this one. Hey, would I be using some type of inclusion exclusion? Or how would I be looking at how to do this? It's just like a step up. I really don't know how to do this last one. How many ways can I do it so that they don't touch? I mean, it's less than the ones that we did, so there are, well, I'm assuming like we'll still do the cases, but we have to subtract the cases where they touch. But I don't know how to mathematically show that they touch. Like, I choose one and then I have to permute it somehow. Don't know. Tell me, dear ChatGPT. remember. Still cases. Let there be 2 blocks. Yep, with positions 1 to 7. So you are choosing at most 3 positions. That's all I need. Okay. At most 3 positions. Yeah, valid. What if I chose that one? Boom, 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 boom. Oh, same thing then, right? C3 choose 1 plus C3 choose 2 plus C3 choose 3. No. Okay. Now I could flip them. C3 choose 3 means there's 3 ways, but I could flip it. Permute them. Permute them. Perm. Perm. No. There's 17 normal ways I could do it. Plus, I'm gonna choose 3 there's 3, and I'm gonna choose 1. And I do the rest. Plus, there's 2. No. Yeah. What else is there? That's the 0th way. That's the 1 way. I'm gonna choose 1 and I permute the rest of the 6. Maybe there's more than 3 spots that I can pick. Like I could choose this spot, this spot. It's like 3. I have to make 3 big ones, and I also have to make sure that there are 3, like I can account for all 3. You're choosing at most 3 positions with no consecutive. There is a choose with gaps. Are you saying that it is going to be... The fuck is choose with gaps? The fuck? Choose with gaps. Fuck you. Is it this one? It is this one. But you can't put it in all 3 spots. What the fuck is choose with gaps? Choose with gaps. Choose with gaps. Choose with gaps. Seven ways. So combination of 7 choose 1, or there's 6 choose 2, and 5 choose 3. Oh, I don't get it right now. I don't get why you did the I don't get the choose with gaps one. That's just not something I've ever heard about. So non-adjacent positions from 7. It's not stars and bars, right? It's completely different. Oof, what a question. Not cool, not cool. Choosing non-consecutive objects. Okay, so if I'm ever gonna choose if we are working with non-consecutive objects, think about the trick is to first force a gap after each square tile. If they cannot touch between every two S's, there must be at least one. Yeah. So before we even decide exact position, square box would require a K minus 1 separating horizontal blocks. Minimum. There are 4 places to put the extra blocks. Yeah, which is 0 of that choice. Choose 2 non-adjacent positions. All pairs is that there are 6 bad pairs. Okay. Minus K plus 1, and then choosing seven plus minus K plus 1 over K. Choices. Forcing some type of non-adjacency. 1 times 16 to the 7 plus C7 choose 1 times 16 to the 6 plus C what, like 7 minus 2 plus 1 2 16 to the 5 plus C 7 minus 3 plus 1 choose 3 times 16 to the 4th. You've got to be shitting me, bruh. Like, I would remember. Forcing mandatory gaps. Wait, show me how to derive it. Because you said 2k minus 1. Like, I get that we're trying to force a gap between them. But mathematically, like, so if I ever counter a question that says, hey, I need to force a gap between them, I'm choosing from a certain of numbers. So we've got a finite and a repetitive set. And I'm just going to force a gap between them by doing, well, there's that many total number of tiles, subtracting the number of choices I get plus 1. What's the plus 1 supposed to mean? Plus 1 is plus 1 plus adding the gap? I don't know, man. Adding the gap? Not really, bro. Not really. Like, sure, but like, you know? So these questions do go from not difficult to difficult. This is a IVT proof, that's fine. Shift left trick. Number of ways to choose k non-adjacent positions from n. Numbers of ways to choose non-k adjacent positions from n. Suppose you choose k non-adjacent positions from 1 to n. Then non-adjacent position means that there must be at least a gap of 1 between two chosen positions. Oh. And subtracting the k minus 1 forced gaps. I can remember that, or I can understand that. Okay, so if got n, then subtracting k minus 1 in a group to make sure we always have the gap. It's just like a modification of the question. Right, so choose, and then choosing from the modified tiles. Everything else stays the same. Everything stays the same. Okay, I can live with that. I can live with understanding and remembering that. So, n subtract k minus 1, c, and k. Is it whatever that they taught already? If it is, now I'm getting it. Bro, this teacher, I don't like, bro. Really don't like him. Obviously, no, it's not obvious. He's been doing it for 20 years. Mr. Happy-Go-Lucky. I don't get it, bro. Let A and B be sets with cardinality A is 42, cardinality B is 52. Let C be the functions from A to B, and D be the functions from B to C. mean, from A to B means the maximum is 42. Cardinal D is 52. Wait. B to C? Yeah. What? Oh my god, bro. You're gonna kill me, eh? I'm sure these are like the unseen questions. Yeah, I mean, I would want to try to attempt them, but not spend too much time on them. Functions that go from A to B. No, if you tell me it's 52 and 42, I don't get it. Okay. Thank God. So I can think of something new. What? How is it not 42? Because if there are 42 elements in set A, then it must mean that those 42 different x values can map to a certain number of y values. You can't get like 43. Oh, I'm stumped. I don't know. What a crazy question. I'm assuming they're not asking me to attempt this question again in the exam. If they do though, it's just like I'm be so mad. Five to the 42? Sorry, 52 to the 42. Oh my god, it's one of those questions again. Core group question. It's those mapping questions. They make me go crazy. Like they're saying for this question, if it's a function, let's take a photo of this. Right, so this is functions. It's just an idea with functions and combinatorics. They're saying I've got 42 in A, right? Got 42 in set A. And let's say that's one of my elements. And I can map it to this. And I can map this one to this. Or I can map this one to that, or to that, or to that, or to that, or to that. Same counting principle, which is crazy. There's more combinatorics functions. Counting principle. For each element in set A, we choose one of 52 outputs to map it to. There is no need for what? No, not inverse. 1-to-1. Just as long as we do one x value to another y value. So and cardinality from B to C. Cardinality from B to C. Wait, there's so many fucking... D are the functions that map from B to the functions. D set contains all the functions from set B that map to all functions from which are 52 52 to the 42 to the 52. You've got to be shitting me. Okay, let's try this. 52 to the 42. 52 to the 42 to the 52. No way, right? But that's true though. I'm assuming for set C. For set C. I don't know. Clueless. Wrong. Why is it a multiple of? Oh, am I a dumbass? This is not the same as 52 to the 42 to the 52. This is, oh my god, my power laws. Oh my god, what a crazy number. Huh. In the following, select all correct answers and only the correct answers. If there's an element in set A, and an element F in set C, and an element G in set D, then the composition of f of A of G of f of A is. Okay, this is beautiful, beautiful work. I'm going to be drawing this out actually. This is a A. $42. Set C from set C contains, here I have to draw it like this. Set C contains all of this. Right, and you would call this set C, and sorry, F is an element of set C, and this would be a function. So that's my element, and this would be a, let's just call it a int value. Okay. I'm gonna put him right here. Okay, and we have G is a set of the function D. So functions from B to C. Okay. You guys seeing this? That means I'm gonna map it. This is set B. This is the same set B actually. That map into these. And we're going to call this G of D. So composite function g of f of a is in set a is in set a. We're going to see how a travels. A travels, we get an element in C, right? So and then it travels from C, but we're mapping that value of C undefined, bro. It looks so undefined to me. So gay. What the fuck? G of f of a. A is a integer, maps to b, and so it becomes a function in C. It's an f in C. Why is there a, okay. Well, this is a function. And I'm putting that function through to sorry, A is right here, mapping it to C, and I'm calling it F. Then G of F and G is an element of D. Well, D is a function. It's an element of D, I suppose. It's an element of C, I suppose. And it's a function from A to B. And from B to C. Fuck. It's not an element of C, sorry. It's a function from A to B, and it's an element of D. Fuck. Is it an element of D? It's not an element of D, but it's an element of C? Okay. No, it's a function. Hey, brother. It's a function from B to C. And it's an element of C. Brother, I'm cooked. It is an element of C. Yeah, I can see that. That part right here means it's an element of C. If I compose it, G of F this outputs a function that I'm going to map from B to C. Have I been thinking about it wrong? G of F of A. Sure, I'll just call it an element of D or something. I don't even know anymore. I'm just gonna guess the element B. It's a function from A to C. It's a function from A to B. G of f of a. It's an element of C. Why is it a function from A to B? A, B, and A. A maps to B. I was trying to find an idea. A maps to B, creates an F, which is an element of C, of set C. And that function, brother, you're killing me, bro. How many injective functions are there from x to y? (18 to the 18). No. They can make 43, 42, 41. So how do I... What happened in my core group? You map 1 to 1. You have to reduce the count. So out of 123 possible input choices, you could choose 123 different starting inputs to map to 165. That's why it's permutations of 165 and 123. So I'm just gonna permute I'm gonna permute 43, 18. Suppose that 8, okay, I need to remember that. These sets are weird, eh? Sets is perms and powers. So for adjunctive sets, it's perms. Suppose that H is a given function from x to z and f is a given injective function from x to z. Suppose that H is a given function. Okay. F is a given injective function from x to y. Then the composite function of g of f let's write out what g of f means. Brother, kill me now. Kill me now. Set x to set z. If f is a given injective function, then g of f. Well, g sorry, h is equal to g of f. Where's my g? Are you saying it's from here? From set D? For all y in big Y, we have that the inverse function, kill me, ah. F is a given injective function from x to y. Không biết nha, không biết nha. 不知道，不知道，对不起，对不起，不知道，不知道，不知道，不知道，不知道，不知道，不知道，不知道，我操！我操你妈的！我操你妈的 mother 傻逼傻逼个傻逼个傻逼个傻逼傻逼傻啊啊 Suppose that h is a given function and f is an injective function. Then if g of f is equal to h is a function from x to z, it's from x to y. H of x to y, and then y goes to z. So for all y, not like that, look like that, bruh. Nope. Y is f of x. Input something into y. Y is f of x. Yeah, this one. Has to be. For all x in set x. Okay, is it because there are 4 of these? So I should just not look at these guys. For all x in set x, then we have that. Not that one. Not that one. The output of y is equal to x of the... Maybe it's like this. Because it's injective. That means we can go y to x. I'm just fucking with you guys. Same number. Nope. Suppose that... You know what? Just know the answers for these. I don't think they're expecting us to just cook these questions up like this. Because I would cry for these 5 marks. Z to the y minus x. Because if g is a composition, if g of f is equal to h, that means g of f of x is equal to h of x. Since f is injective, the elements, the output values of f of x are all distinct. So g is forced on exactly the number of cardinality of elements of y. Wow.
No, I'm not gonna know that. Now we have some floor function. Okay. Where GT is the some number between the set of 1 to 32, square that and you take the floor of that, and we're mapping it to we're mapping it to the integer domain. That's fine. And H is a inputting some number between 1 and 34 and also flooring it by 15. Then if G of F is equal to H, where's F? Once again, they're talking to us about if G of F is equal to H, then G of, the F doesn't matter, but it's G of something outputs T. Let's do F of X gives me H of S, or gives me H of S. Okay, well, H of S is a integer. It's equal. Okay, so it's one of these two, I'm assuming, and it's F of S is in some element. I'm assuming it's that. Nope. Could it be? Nope. A single 10. You're gonna kill me, bro. Wow, I just picked everything wrong. Nah, bruv. Don't play with me, bruv. If y is larger than 8, then y is... So that's 8. Then y is less than f of y. They are all, if y is larger than 8, then they are all you're giving me this function and you gave me an output. It says, hey, if y is larger than 8, which is probably here, right? Then these guys are all I see a hint here. It says positive. Well, if it's positive, positive, negative, if we bro. I can't be bothered, bro. If our output is less than -8, like that, then the output -4 and the output -8 and the output +8 are all non-positive. If we add y, we still get it. The function is sometimes increasing or decreasing. Suppose prove y is onto using the IVT. Suppose y is an element of the range of f. If y is less than 8, then we have, there's so many values. Like right there. If y is less than 8, there's so many values, bro. It's, sorry, if y is more than 8. So we're looking at what? -8 to 8. If y is smaller than -8, we're looking at values of the same shit. Otherwise, we'll have f of a and f of b is what? You're showing me a weird ass function. What, this is a is minus 8. Are you telling me it's like there? Or I don't even know. What, like 4 to 8? Right. If it's less than minus 8, which is like there and there and there. If y is less than minus 8, we're taking values from here on out, no? Bro. I don't get this question. I don't want to get it. I don't want to get it. I don't want to get it. I got enough for today, bro. I'm gonna do my set in a bit, but like, yeah. Those questions involve why. Fuck. Nah. Nah, Burv. Burv, nah, Burv. Burv. Brother. Minus 8 goes to some f of y. Không hiểu. Không muốn hiểu. Sẽ không cần hiểu. Don't worry. Câu đó không ra đâu. Câu đó mà ra thì thôi. Wow, those questions really fucking not cool. Combinatorics, core, recurrence, tiles. only part to remember thoroughly is finding C2. And finding C2 was like, if we chose one of the 17 ways and did it twice, it would just be inside the 17 times an ways, so it's redundant. For the C2, it was like there were a total of 9 ways, and we'd force it to either we'd force it to be this way, because if we put any horizontal tile down, the next move to fill the other horizontal was to put another one of 3 horizontals in. If they know what I'm saying. This was a good proof. Proof of composition of sets for bijective function f. I could just like, yeah, if I do come across it and I'm gonna revise, read the proof in our thingy. Oh, super hard one. Proof of dual and non-dual, and proof of dual and non-dual formula for using, proof of planar graphs having a upper bound of edges using Euler's formula. Combinatorics using tile grids. Turn it into 7 tiles, or 7 2 by 2 blocks. There are 7 independent choices and 17 ways, because it's one way add for the non-numbered, and 16 ways to group the other 4 each into a square and then choose. Partial combinations and adding them together, like case without tiles, without unnumbered, with 1, with 2, with 3. Third one is way to force choices of the unnumbered box to have a gap between them. Suppose there are n objects, there are n tiles, or there are n places to place them. and we subtract and we subtract by k minus 1. So we effectively force disconnection by saying, hey, I've got these many or k things I want to place, and I want k minus 1. Somehow it works. So the rest is the same. C n minus minus k minus 1, and then k choices. Stupid question. Functions. Unseen functions. Bro, if they give you this, it's like, I mean, I didn't see those other guys do it. I mean, I didn't see that one in the final exam. Weird, eh? IVT, but with outputs? Oh, I could have. You're right. I could put the functions in here. Oh, I get it. If I put something that's larger in here, right? Then we have a positive number here, a positive number here, and a positive number here. Right? If I put 8, this cancels, we still have a positive number. If we add y to both sides, what do you mean you add y? Then y is less than f of y. I think they're talking about this one. If I put 5 in, I get 1. Sorry, if I put 9 in, I get 1 times 5 times 17 plus 9. So that's our y. What do they mean about adding y to both sides? Sorry, this is IVT with outputs. Yes. So this is like some residue. It's always some residue. If I add y to both sides, it's always some residue. It just means that y is always smaller than the residue, just because they set up the function that way. Because there's a y here. Same thing. If we add y, it'll always be larger than the negative residue. Okay, we should just look by part A and by part B. Nuh-uh. Okay, I will see you guys in like, what, 10 minutes, 20 minutes? And we will be back for the set E, our final set before we dive into the world of combinatorics for the night. We do everything we can about combinatorics. Yay. We'll just put this right here. We have 19 questions. Partial orders. Encryption. Oh, sick modulo questions, eh? And eventually increasing. Wait, I've done an eventually increasing question. Well, it looks like cosine is oscillatory, so it's not eventually. Oh, there exists some p larger than some number such that it's always going to be a certain thing. It's like if you add enough floor fractions, there's a existence of a number. I've done that one. Britzian alphabet. Dr. Britz, eh? Right. Tons of function proofs. These are free marks. These are free marks. Gotta grab them. Bunch of free so they always give like logic and graph questions. I'm assuming it'll be the same for the final. Okay, stream is paused. Let's go like 3 hours maybe. And we GG's. Sorry. No, nothing. Huh? Wait, what? Check va. Check va. Sorry, my bad. These ones are like fine, you know, given that proves this by completing the isomorphism below. Which one's I? Which one's J? Okay, I, J. Ooh, sick. This one has 5. As does this one and this one. So G and L are the ones with 5. Right? B, E. Well, B has G, so E has L. Right? And E is connected to... Okay, both of them are. C is on one end and D is on the other. So it's a choice between the two. I'm choosing between K and... What is this? K and I. K and I. The only thing that's different is I is related to H, as is D is related to A. So this must be I. The other one's K. I think they'll always give us truth tables to work with for the free marks. So we don't want to fuck it up. True. Q implies R, that's true. So if this is a true statement, that's true. And that is... Oh, are they asking if it's logically equivalent to this? Sorry. P and Q, true, implies R, also true. So these... And are these two logically equivalent? Sample E, right? Sample E. Is P implies Q implies R equivalent to P and Q implies R? P implies not Q or R, and implies and since it's like that, I could do this, and it's like that. And this is the same as this.
which is, so they are equivalent. TTF, well, if this is true and false, then this whole thing becomes false, and it's a true statement implying a false statement, which is false. It's the only time that it's false. And a P and Q, that's true, implying a false statement, once again, is false. I'm assuming that's also false. Or are they equivalent? Honestly, it looks like they are. It says P, which is a false statement now, implies anything. So it's gonna be true. It's probably true. Okay. So that means there is some type of... Oh, it has to be logically equivalent. Okay, fine. The truth table shows that this is a tautology. This one. Tabitha does not know how to fill in tables, so she randomly picked T and F, or at least for each of the 9. How many different tables should she end up with, which at least one column contains no F? So it's a column. What do you mean a column contains no F? Let's just strip of the thing and just go to 3. Each time she can make a choice between T and F, right? And how many tables would she end up with, which has at least one column with no F's? So we just want to take all the 2 to the 9 ways that she's going to do it, and we're going to subtract it by the times where there are no F's. So cases of no F's sorry, what? How many possible tables could she end up with which at least each column contains, at least one column contains no S and no F? So she could do, okay, I mean, all column, no F. So she's trying to do no F. Right, so less than or equal to, we're trying to subtract this. So subtract columns, subtract tables where there exists columns could she end up with which at least one column contains no F's? So there are no F's in the column, and they want the tables where there is an F. What the fuck am I reading? Tables where there exist columns of F. How many different possible tables? So, there is a column that has that. At least a column of this. Oh my god. How about this? We just say, hey, there's one choice for all three of them. No, that's fine. One choice. Choose by column. One choice. This is case 1. 1F. Case 2. 2 columns. No F. Case 3. All F. All T. So this is one case. This is... You can permute the other ones any way you like. 2 to the 3rd. And the 2 to the 6th. Right, so 2 to the 6th plus 2 to the 3rd plus 1. Please, bro. I'm cooked if I don't know. There's 2 to the... minus tables where there exists columns that contain F. Wait, no, is that right? There are tables where there exist columns that contain an F? No, too many of those. There's a choice I could make. I don't know, man. If it's a much bigger one, it might be like a whole one here. So okay, one, it could be here, and then 2 to the 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 16. 2 to the 16 ways of choosing other, or 2 columns, which is 2 to the 8 ways, or all 3, which is 1. So 2 to the 16 plus 2 to the 16 plus 2 to the 8 plus 1.
Nope, I don't know then. Double cooked, triple cooked, quadruple cooked. Don't know it. Sorry with the hair. What is this? Oh, sorry. So it's inclusion, exclusion. Ew. Don't know. Don't get it. We'll try to understand it. We are starting with choosing a column, one choice, 2 to the 16th, nope. 2 to the 2 to the 2 to the 6 ways. Oh, okay, they're saying group that one together, choose one of the 3 columns. One choice. One column, 3 choices. Then 2 to the 6 ways. So choose a column. Where all is T. 3 choices from 3 columns. Then there are 2 to the 6 other ways.
to put T's and F's down. But I don't know why, must consider that you could accidentally get a case where you put T's, all T's in one of two other columns, and one case where you could put all T's down. So what are we subtracting? Right? C3, choose 2 for full columns. How do we incorporate this part in? Must consider that you could accidentally get a case where you put all the T's in one of the other two columns, and a case where you could put all the T's down. So I subtract cases when I put two of them down for full columns and 2 to the 3 ways. Then consider you. Yeah, okay, I understand it now, but is this a type of inclusion exclusion? And would I just come up with this by direct counting? Then consider the time you accidentally have all 3 T's. Add the case where you have all 3 T's. Why they come in contact with all this so fast, eh? Right, so combination of 3 choose 1 times 2 to the 6 minus combination of 3 choose 2. This is inclusion exclusion. How would we write it? I would do sets. Set of column that has all T's, set of column that has 2 T's, set of column that has all T's. And I'm going to try to write it. So set C1 column, a table. C1 is tables with one column, full T's, or no F. C2 is tables with two columns, full T's. T3 tables with three columns, full T's. And inclusion exclusion is C1, the union of all of these is equal to the universal set C1, C2, C3, minus C1, oh. What's the other way? Do it by complements. Teach me complement. So C1, the set width is what? Full column with T and like full here. Tables with one column. No, table, sorry, it's just column 1. You could just say column 1, column 2, column 3. Sorry guys. This just means full column with 2 to the 6 other. Same one here. Same one here. So that means three cases. And then 2 to the 6. Subtract 3 cases. Where we got 2 columns. and and 2 to the 3, add 1 case, 2 to the 6 minus 2 to the 3, plus 1.
I could do that times 2 to the 3 plus 1. What the hell? They don't let me do that here. What's the other one? Complements. Each column has 3 blanks. So each column has 2 to the 3 minus 1 ways to avoid being all t. There are 3 columns. So there's 7 to the 3 ways to avoid being all t. At least means at least one column is all t. At least one column, so tables with at least one column of no f is one column with all t's. To the 9 total ways. Subtract when there are columns with f. Oh, there are columns without any t. One column could have 2 to the 3 choices. So like TFT, TFT, FFF, FTF, something like that. It could have 2 to 3 choices. We want to exclude times where it has no t, or FFF. 2 to the 3 minus 1 is 7 choices that
One column could have 2 to 3 choices, like T, F, T, F, F, T, F, T, F. And we are trying to subtract when there are columns without any T. So we want to exclude the times where it has no T, or only FFF. So there are 7 choices of, tables with at least one column no F, one column all T. One column all T, one column all T. Looks like that. 2 to the 9 ways subtract columns without T. Subtract columns with full F. When there are columns without T. At least one column no F. One column no F. One column no F. One column without F. At least a column without F. At least a column without F. Tables with one column Okay, subtract when there are columns without any T. Yeah, okay. Subtract columns when there are no columns of T. Because we want at least a T in there. How many tables could she end up with at least one column that contains no F? At least one column no F means at least one column is all T. Every column is at least one F. Complement is, we're trying to find the complement. Every column has at least one F, and we're subtracting the times that there is a T. Subtracting times where there is a T. Subtracting times where there are T's, because we want to, nah, the other way is better. Case 1, all T. 2 to 6 other ways. Account for 3 of the other ways that you can choose.
Yeah, I'm better off learning the other way. I can't wrap my head around it. Nope. Don't play with me. Don't play. Don't play with me. It's too late, brother. It's too late, brother. Bruv, yeah, bruv. Yeah, bruv. / page. What's this? Combinatorics and logic. Oh my god, what a stupid question. I don't like this question. The question is asking is how many possible tables could there be such that the table would have at least a column full of t's. Or using the complement, let's say there were 2 to the 9 choices. Then the tables where at least one column contains no F. Then the tables where then subtract tables where there were full F's, because we don't want that case. There's only one case of that per column, which is FFF, and we want to get rid of that. Sorry. No. Contains no F's. The other ones still contain F. Saying there's only one case for which is no. There are so many. There are 7 cases. There are no. Subtract the tables where there are F's, which are the 7 cases per column, right? So everything but the TTT, subtract it. There are 7 cases of this when there's an F or 2 F's or 3 F's in the column. Subtract from 2 to the total 9, 7 to the 3. You can make this choice. Fuck! And fuck ChatGPT, bro. Fuck this question. Is it bipartite? False. Wait. An Euler trail is exactly two odd vertices. This odd and this odd. This has even. The graph G contains a Hamilton cycle. That means it goes everywhere and backwards. False. And the graph is bipartite. Well, what's the definition of a bipartite graph again? Can they be partitioned into where two no vertices are adjacent? That one, and that one. Okay, that's true. Fuck this question, sorry. These would give us free marks. We do not want to lose these marks. Oh my god. Shortest path from vertex A to every other vertex in the following graph. AB. Next vertex is B. Total distance to this vertex is 2. B, well there's 3 cases, right? B7, B9, or B7. Right, BD. We're in a D. And that's 7. Oh, 9 total distance to this vertex. Wait, let's see if... Okay, so it's 7. Oh, what the hell? You think this is wrong? Oh, which gives the shortest path from vertex A to every other vertex. That's why they're saying AD. And I could go C this way, so I could go to C like that. What? I'm going to AD automatically with 5. I can go to AC. I want to go to C now. Looks like I'll go like this. I also go to AD, and the total is 8. Okay, let's try to get to E now. How could I get to E? If I go here, that's 11. I go here, that's 13. If I go here, could I go here? 5, 1, 1, 4. What's that? 11. I just go straight there. There's no shorter path. So I can go to AB, go to E. Which is 11. Let's just check. What do you mean, bro? So why the fuck am I going AB and then AD? Do I go DF? Motherfucker. DF. We're going to F. That's 1. Right? I can go to FG. Another one. I could go to FC. Okay, it doesn't want me to go FC. It wants me to go. Could I go G? Could I go GE? Couldn't go GE. How am I gonna get to E? BE. Don't fucking play with me. How fuck am I gonna get to E? Brother. Huh? Okay, I'm gonna pull up Dijkstra's algorithm. What a weird thing. So like A goes to this goes to F, so that's 6. FG goes to that, goes to that, goes to that, so that's 7. My next stop is what? So we're sitting at G right now. Right? G can go to here. F can go to C, right? Can F go to C? F can't go to C. Okay. G has to go to E. Nope. That means it's quicker to go from A to E. Sorry, from B to E. That's 11. So we've spanned. This is fine. Now we want to try to get somewhere F in the shortest time possible. Like that's faster to get to C, right? F can only go to H and G. Could we go to C faster? We haven't got a C. That looks like the shortest path to C. A to D and then D to F, F to C. Right? 5, 8. There's no faster way to get to C, bruv. 9? C to F? Oh, CF vertex is possible, right? Eight. GJ. I'd rather go forward.
I went ADFG, I'd accumulate 7. So going ADG, which is 9. If I went ADFG, I could go to J, GJ. But if I went ADFH, I'd accumulate 14. FH looks fine. Then get to here. Looks like I'll be looking at these three. Well, 5, 1, 6, 14, 20. 5, 1, 6, 14. 5. 6, 7. 13. We're going JK. 5, 9. 5. No. 5, 7, 8, 15, 18. If you get what I'm saying. What the fuck? Wow, I don't know how to use Dijkstra's algorithm. Doesn't matter the tree? What the fuck is he saying? Okay, we got a thing in there where we're going A to B, which is 2. We could go A to D, which is quicker than going A to B and then D, which is 5. We can go A to D to F, which is 8. Oh, which is 6. We can go A to D to F to G, which is faster. We can go A to D to F to C. CF is a good one. CF is supposed to be like right here. CF is supposed to be right here. Right, and we're going to C right now. If we accumulate it that way, we should see that this grows in a line. Because he's taking 1, 3, 4, 5, 6. If we're going to C, we're going to get to 8. After we get to C, we're like, hey, okay, I'd rather go from F straight away to H. So I would go F to H. Then my next move is H, and that means I accumulate what, 14 max. Yeah, H. I accumulate 14 max. Okay, now I'm thinking, hey, I could go here. Sorry, that's actually faster. I'd actually go from G to E first. We're gonna E. Right? 6, 7, 11. Then I go from F to H. Which is that. No, sorry, that. Which is 14. And then I go F. If I went F to H already, I'm gonna go G to J. And that take 15. Right? 7, 15. Oh my fucking god. Stupid ass question. Weird ass question. So Dijkstra's algorithm. Dijkstra's algorithm must be choosing in order from total distance from A to the specific vertex. So analyze the different routes from where that intermediary
point was to your next vertex. Pain in the ass. Oh my god. That took me a little bit more than 2 minutes, eh? How many edges does G have? Planar graph. It has this degree sequence, so it should have this many edges. Never mind. One. It has a half of this edges, which is 6, 10, 12. It has 6 edges. How many regions does it have? It has the same amount of regions as it does vertices, not degrees, vertices. 7 regions. Sorry, 8 regions. Ew. We have to draw it. I'm pretty sure it's 8 regions in a planar map. This is G. Oh my god. How many regions does a planar map have? It's probably n plus 1? Or sorry, vertex plus 1? No, actually don't know then. It's not 7, eh? Can't be. You have to draw it. Well, this is degree 1. Connect. It's another degree 1. I'll draw it. Maybe the number of regions. Simple. Connected. Oh, okay. And planar. Let's see how many regions G has. Oh, my iPad is dead. You know what? I'll go conventional. Right this instant. Okay. If we had a vertex here, a vertex here, a vertex here, 7, right? Vertex there, vertex there, vertex there, 7, like that. It's connected, so that's 1. This one's connected to this one. Let's see. This one has degree 2. We'll just make this one degree 3. So there's 3 degree 1s right now. Well, I guess I can't do that. No, it must be okay. Never mind. This has to be connected to that. This has to be connected to this and connected to that. So it actually looks like a tree. This one has degree 3. 1, 1, 1, 2, 2. And it actually looks like there is one region. G has one region. I'd have to, yeah, I had to see that it was planar, so I was gonna draw this tree of a fucking diagram. Sorry. I'm just hating fucking my life right now. I don't wanna study. What? Planar graph. Kruskal's algorithm. Pick one edge that can be chosen as the first edge in Kruskal's algorithm and enter the number of labels on the vertices. Okay. So 1, 2 could be a possible edge. How many choices of the first edge are there, including the one you chose? 1, 2, 2 choices. What is the weight for the minimal spanning tree? We're going to choose this one, choose this one. We have to choose that one, 13. We're going to choose this one. 13, 15, sorry, 13, 18, 23. Fuck me. Boom. This one. I take these two. Sorry, what? I'm gonna take this one. I'm gonna take this one. I'm gonna take this one. I'm gonna take that one. And I have to take 9. I didn't add 9, my bad guys. I have to add 7 as well, my bad guys. 3, 13, 18, 23, 32. Very much heavy marks relate. I don't know. Heavy marks related. Why are they doing these Google Gaga questions that I'm still failing? Okay. Given a positive integer, if x is a perfect square, then for all prime integers p, there exists an even integer a such that p to the power of a divides x, and p to the power of a plus 1 does not divide x. Okay, if x is a perfect square, hi.
Hey Alex, let's go. What I have
Hi.
right now, it's a one-man company for the, I guess, 3 or 4 years. I just kind of lost something. Yeah. So I just wanted to know your why you are doing what you are doing.
When I was 22 years old, I'd had a good weekend and I started work, and a person in my past, she said, "You're in a good mood." And I was like, "Yeah, it's just, you know, had a good weekend." She was like, "I'm pretty sure the secret to happiness is living as many days in a row like that as you can."
Hi. Ê, ngủ đây 20 đô. Ủa, đẹp thế. Hi. Đẹp vãi. That's pretty nice actually. Wow. You know what's đẹp hơn? Your hands. You know that, right? I got this necklace nowhere. Hi. What you doing? Hi, baby. Sorry. What you doing? You about sleep? About sleep, bruh? What I ate today. We get engraved. If you want, I'll give you that. Ooh, maybe. Show me, show me, show me, show me. My E, okay. What you gonna do now? The contrapositive of the above statement is there exists X is not a perfect square if for all primes there exists my E ngủ. Okay. There exists an integer such that contrapositive means we are trying to say the same thing but in the other way, which means it's not a perfect square if there doesn't exist an even integer such that it doesn't divide P doesn't divide X and P divides X. X is not a perfect square if for all primes there exists. So existence is fine. It's just the yes or no's here. I'm gonna get this. Okay. X is not a perfect square if for some prime or X is not a perfect square if for some primes with an even. Okay, so the alls and evens. Hi. So the negation of that, even is okay, right? Hi. PA doesn't divide X or PA divides PA plus 1 divides X. I've got to practice this one. One's a good practice one. Dijkstra. No. Minimal spanning tree. This one we got to practice. What, like contrapositive statements? I am Bridge, the sun is shining, harbor is inviting, my boat is at the mooring, my friends are happy. If the sun is shining or my boat is in the mooring, then it's an implication. So S, what, like S or B implies H and F. S or B implies H and F. S or B implies H and F. If the sun is not shining or the harbor is not inviting, then my boat is at the mooring. Hey, what? What the hell? What the hell? Bông hoa và hình trái tim. Okay, I will wax. I will wax. Bên này là hình trái tim, bên này là hai bên này là hình trái tim, bên này hình trái tim, bên này là bông hoa. Ok, đã hiểu. You like my armpit? You like my armpits? Yeah, you do. Why you look at them?
Because you showed me.
Oh, okay. I'll turn off my camera. If the sun is not shining. Oh, this one for sure. Oh, what the hell? That should be H and F. If the sun is shining or my boat is at the mooring, then the harbor is inviting and my friends are happy. Why you middle finger me? If it's shining or my boat is at the mooring. Wait, why is there something that looks exactly the same? These ones look the exact same. Are they dumb? Brother, ugh. Brother, error. Sorry. Trình ngáo đá lắm rồi Christine ạ. Khổ thân thật. Mấy con này khổ dâm quá. Let R be the relation on the set of integers defined by A is related to B if and only if A is B squared. Then what are the options that are true? What A is not equal to B squared? What A is not equal to symmetry? It looks like R can be symmetric because 1 is equal to 1 squared. Is it anti-symmetric? If 2 is equal to... If A is related to B... So if A is related to B, then B is related to C. I can see that happening. Like 2 is related to 4. 4 is related to 16. Then A is... Oh, no. Can't be something squared, can it? Could it? What the fuck? Why the hell is it anti-symmetric? Ugh, kill me now. Kill me now, Christine. Kill me now, Christine. I want to die. I really want to die. It's not for kids.
I give you a list.
What?
I give you a list.
You give me a wish? A what? A leash? Why leash? To be a sick chó? What? I don't get it. Why a leash kill me? Những người tà dâm có quỷ đi đằng sau. Hãy chỉnh lại sự phu đốn của bạn. Bạn hãy là một người đi theo nhà Phật giáo. Hoàn toàn bình tĩnh. Why the fuck is it anti-symmetric? Cause it can't be the other way, eh? Like it has to be bigger. But it's a set of integers. Okay, since integers, in most cases, when you square something, it's gonna get larger than the previous. So I'm assuming that's why it's anti-symmetric. Oh, what? You open your camera? My bad. Oh, sets and relations, I'm assuming. Let R be a relation, then R is said to be anti-symmetric when if A is related to B and B is related to A, then A is actually equal to B. And that's the only case. That's when 1 is equal to 1, because any other that is two elements of A may be related one way around or the other, or neither, but never both. You hear that? Alrighty. A few examples is the equals, mate. Mate, it's the equals, mate. Mate, brother. Okay, we are working. Show that it is not injective. I am cooked. One first cooked question. 2 cooked questions. 3 cooked questions. 4 cooked questions. Oh, another non-core question that will come out. Another core question here that is coming out. Jesus Christ. What a hard exam. That means they really want you to get everything right up until this point. It's about 21. Yes, babe? Cái gì vậy? Căng vậy? 11 tháng 5 chia tay là Ani mấy? Tại sao chia tay vậy? Sao chia tay vậy? Đâu có đâu. No, I didn't. That would be a long time. That would be 1 năm 8 tháng. You're so cute. Think about this.
counterexamples maybe? The floor of that. What does the floor of that look like? Sure that G is not injective. Oh, to show G is not injective, then we need to disprove that f(x1) is equal to gx1 choose what? Two minus 1 on 2 is equal to 1 on 2, and the floor of 1 on 2 is 0. Choose one minus 1 on 2 equals 0. Choose y1 equals and y2 equals 2. Then floor of and g y1 equals 1 minus floor of 1 minus 1 on 2 and g NG so I love you, Christine. You're my baby. I love you. I miss you. Wanna kiss you. Haven't kissed you. Nin E. Okay. I wanna be like that raccoon. Hello. Is that Gru? Yeah, it's Gru. Cute. Cute. Subtail. Aw, did you send me hearts? Aww. 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 Why you cry? Okay. G of f of x and f of g of x. Nope. G of f is equal to g of f of x is equal to the g of 2x plus 3, which is floor of 2x minus 2 on 2, which is floor of x minus 1. And f of g of x floor of x minus 1 on 2. So that's floor of this function 2 times the floor of x minus 1 on 2 plus 3. I'm assuming that you can cancel. Oh fuck, I'm cooked. But you said the simplest term. Okay, I guess I can't do fucking that shit. What, like 2x minus 2 on 2? That is floor minus 1, you fuck. G of 2 of x, put 2 of x into here. Minus 1 on 2. But that's wrong? Gotta be shitting me. G of f of x is the floor function. What do you mean that is the simplest terms, you fucker? About 2 times the floor of x minus 1 onto plus 3. But that's wrong. How? 2x plus 3 into y, which is 2x plus 3 minus 1 onto floor, which is floor of 2x plus 2 onto
Oh, it's a plus sign. I'm a dumbass. Jaden, are you a dumbass or a dumbass? Oh my god, you're a dumbass, Jaden. Jaden, you're so fucking dumb. Oh my... G off inverse. Which means we're looking at this floor function here. This floor. Why'd you end the call on me? Wait, 1 second. Wait, why you pinned the photo? Why you pinned the photo? That's crazy. Why you pinned the photo? Why you sad? Ngứa đầu quá em ơi. Oh, you thought it's cute? No way, really?